everybody, it is I, your all-time favorite sex god, Richard Blyle, here with my second of 4 thermodynamics videos. Today's topic, the first law of thermodynamics. Now, I told you last time with the 0th, and by the way, over 100 views on that, which is pretty impressive because I am not a teenage girl. Anyway, if you are returning for the second video, thank you so much for your continued patronage. The first line, I promised you last time a couple of things. I promised you this would all feel familiar to you. This is no exception. The first law, you know the first law. You've been hearing it your whole life. What you've been hearing is wrong, which brings us to the second point. I promised you that I would expose the truth about these laws, and I'm still going to do that. This may blow your mind a little bit. May not, I don't know. But like I say, when we teach, we present this package to you that looks complete and beautiful and pretty, but we don't show you where the paper doesn't quite fit. We don't show you where the packaging is kind of messed up a little bit from the transit or got a little bit soggy. We're going to look at those mistakes. We're going to look at some of those issues here. First law of thermodynamics. Now, if you recall, in just a real quick recap, we talked about the 0th law of thermodynamics in the last video. Why it's called the 0th law of thermodynamics. And the only thing that the 0th law tells us, really, and we learned a couple of definitions. We're going to learn a couple more today. And we saw an equation. We're going to see equations today. But mainly, the 0th law simply says that heat will transfer from a region of high temperature to a region of low temperature. It's really all it says. And we looked at what heat was in the equation for change in heat and all that fun stuff. The first law of thermodynamics is probably one of the most familiar ones because the first law is simply the law of conservation of matter, which is it's a little bit, it's kind of you've been learning about the law of conservation of matter basically your whole life. You learned about the law of conservation of matter as soon as you started taking chemistry or physical sciences. Anything that talked about chemistry, we talk about the law of conservation of matter. Guess what? Neither one is correct. Einstein. Nobody likes a show-off. Come on, Albert. What's your deal? Everyone knows you're smart. You don't have to rub it in. Just trying to adjust my camera a little bit. Albert Einstein actually wrote this tiny little equation, of which you are probably also familiar. E is equal to mc squared. Now, I told you last time, the laws only really apply to the confined conditions under which they are construed, under which they were created. We're talking about equilibrium thermodynamics here. This is nuclear physics. This is outside of the realm of traditional equilibrium thermodynamics. This falls into the realm of nuclear physics, which is well beyond the scope of these discussions, but notice this. Einstein showed us that if we annihilate a certain amount of mass, we will get a certain amount of energy. Well, you know what that means? That means that energy is not constant in the universe. Energy can be created in nuclear reactions. He also explains that the amount of mass is not constant in the universe. Kind of an interesting thing. We're not going to go through these calculations, but if you take the mass of protons, the mass of neutrons, and the mass of electrons, and add them all up for certain elements, for any element honestly, you calculate what the total mass ought to be and compare that mass to the experimental mass, you're going to find a discrepancy. The mass is off for a little bit for pretty much everything, actually maybe even hydrogen. I'm not sure about hydrogen, but it's usually off just a little bit. Where does that mass go? It goes right here. That mass is the energy that holds the nucleus together. And when a nucleus falls apart, or when a nucleus is created by smashing smaller elements together, there's a certain amount of energy that is released. That energy, to a very good approximation, becomes this mass. I actually did create at one point a video that did discuss this. It was a video about how to make your own, how to annoy your neighbor, how to annoy your enemies and amuse your friends by making your very own fission, fusion, fission bomb. It turns out it's a lot easier than you might think, but it's also impossible. Not impossible because it's been done, but for you and me, yeah, we're not going to be able to do it. So the first law of thermodynamics basically tells us that the energy of the universe is conserved, which again, a really good approximation, but just that. I mean, you will never see an exception outside of nuclear physics where any difference, any change, any inaccuracy in this law, you're never going to see it matter. It's never going to be significant unless you're a nuclear physicist. And again, we talked a little bit about systems and surroundings. Remember the system? The system is the region of space under consideration. So I can talk about this water here as my system. Surroundings is everything around that is not in the system, and the universe is the system plus the surrounding, which is everything. So if we were to have a change in energy, there's a guy named Thomas Joule, Joule, Thomas Joule, who did a very famous experiment. He had apparently a ranch with a laboratory underneath it, and he had horses. And this is my sad rendition of a horse. That's a little ear. And my art friends are pretty much rolling their eyes right now because I clearly have a problem with scale in my art. So here's our horse. Here we have so many people who are in the road right now. So many drivers fit right there. Anyway. No, that's a tail. That's not what you're thinking it is. Anyway, put the horse on this walker. I think you've probably seen these. It's just an arm attached to an axis. And the horse can basically walk around that. It's an exerciser. But Joule did something a little bit different. He ran this post down into his lap and attached it to a paddle, which he sunk in a big container of water. This is how I draw water. So as the horse is going around, they're doing work. And they're stirring this big tank of water, which had a thermometer in it. Now, talk to my physics friends. Yes, I have a friend. And ask them what work is, and they will tell you, well, work is equal to force times distance. Force times distance. I can push on this wall. I can apply force. Actually, I have an old teaching injury. I used to throw myself against the wall to make this point in my lab, and I actually injured my shoulder doing that. Anyway, but if this wall isn't moving, which it is not, I can assure you, not doing any work. I'm exerting a force uselessly. Well, here, there's a certain resistance in this system, especially caused by the water. This water is creating a resistance because the horse has to move that paddle. So there's a force required for this horse to walk. And by measuring the number of times the horse walks around and knowing the radius of the circle around which the horse is walking, he knew the distance. Work times distance, so force times distance. He could measure the force experimentally, so he could measure the total amount of work being done by the horse. And what do you think happened? Down here, the water started to heat up. He proved that energy can be converted into work and heat. Work and heat are interconvertible. Now we do this every day, most of us anyway. Went to see my friend today. Yes, I already did that one. Went to see my friend today. Managed to have lunch with her. I was so happy to have lunch. She's my best friend. I love seeing her. But, got my car and I drove. And what do you do in your car? Well, if you have a gas engine, you're burning gasoline, which is generating heat, which is being converted by the engine into work. So heat and work are interchangeable, interconvertible. Now, if indeed energy of the universe is conserved, that means that delta U for the universe must be equal to 0. We're not allowed to gain or lose energy. Unless you're a nuclear physicist, in which case you're probably laughing at me saying, I can! Bite me. Anyway, total change in energy is going to be 0. First law of thermodynamics. But heat and work are interchangeable, so I can rearrange this. Like this. The amount of work we can get out of a system is equal to the negative of the heat. And we know what heat is. From last time we learned that heat, doing this under constant pressure, is mass, which would be the mass of the water, times the heat capacity of the water under constant pressure times the change in temperature. And now we know the definition for work. First law. Now, we're not going to go into a lot of calculations here. There are a lot of calculations you can do. But let's talk a little bit about chemistry. Because in chemistry, well, like your gasoline engine. Like your gasoline engine. There's a certain amount of stored heat in your gasoline, a certain amount of stored energy. Chemists call that enthalpy. Enthalpy is what we use when dealing with constant pressure. Enthalpy can be thought of as chemical energy under constant pressure. So if you're burning gasoline, gasoline is measured in octanes. Octane is a chemical. Now, what you are burning is not octane. It's a mixture of what we call hydrocarbons, which means it has carbon and hydrogen. And your octane rating is basically telling you your quality of gasoline compared to pure octane. So 100 octane would be the equivalent of burning 100% octane. When you are burning, let's say 89 octane, that octane is burning with an efficiency as if it is 89% octane. That's what it means. In any burning process, means that we are burning in carbon dioxide. In oxygen. We're burning it in oxygen. That's what burning is. Now, burn any organic compound, like gasoline, like gas piped in for your heat or your oven or what have you. The products are always the same. Now, I have to mention here, when you burn anything, when anything burns, there's a certain amount of carbon monoxide that's given off. Carbon monoxide is deadly. Carbon monoxide binds to your red blood cells, basically causing them to be inactive. If carbon monoxide is bonded, your red blood cells cannot carry oxygen or carbon dioxide. Regular respiration, your red blood cells picks up oxygen in your lungs, goes down to your cells where the oxygen is held onto loosely enough that the oxygen can be released. In the cells, your red blood cells picks up carbon dioxide and returns back to the lungs. Again, carbon dioxide held weakly enough that the carbon dioxide can be released where we exhale it, and then the oxygen, which we inhale, can be picked up and the process continues. Carbon monoxide never releases, causing oxygen deprivation. While you're breathing, you're suffocating while breathing, which causes headaches, drowsiness, sometimes nausea if it's really bad, death, and once you're dead, there's not a lot we can do for you. So, I recommend everybody, especially if you have gas piped in, or oil, heat, or coal, if you have a fireplace, if you have an attached garage, get a carbon monoxide detector. Put it somewhere high. I would recommend more than one. Put it somewhere high, so if you have a gas furnace in the basement, put it high near the doorway to the basement. Because carbon monoxide is lighter than air, it will rise. While you're at it, get one and put it high in the main floor, and then get another one for your second floor, put it high in the second floor. Anyway, usually what you get is carbon dioxide and water. Now, I am a chemist, so I have to balance this or it will drive me crazy. If I happen to know I needed 2 here, gives me 16 of these. 18 by 2, well, that gives us 18 of these. Now we have 32 oxygens plus 18 oxygens, 32, 40, 50, which means we need 25 oxygens here. That's our balanced equation. Where does the heat come from? We call it chemical potential, but where does that heat come from? If you really think about it, all a chemical reaction is, it is a rearrangement of the chemical bonds. Okay? It's a rearrangement of the chemical bonds. So we have, because we have a 2 here, we have 16 carbon-carbon bonds, carbon-hydrogen bonds. We have 36 of those. We have 25 oxygen-oxygen bonds, which is a double bond. And no, I'm not going to go into this. On the other side, on the product side, we have 32 carbon-oxygen bonds. which is also a double bond, and 36 oxygen-hydrogen bonds. When I write 3H, 36. 6. All right. I'm going to tell you a truth. There are very few truths in science. This is a truth that is going to blow your mind, and I'm going to really piss off biology professors. Because it seems like I have never known a biology professor that teaches this the correct way. Never. Anytime you break a bond, it costs energy. You have to put energy in to break a bond. Anytime you form a bond, you get energy released. Okay? The first law of thermodynamics also tells us that energy tends to go from high to low. It tends to try to minimize the energy of the system. We see this in physics all the time. That's why balls roll downhill and not uphill. It's trying to get from a high potential energy to a low potential energy. If it costs us energy to form a chemical bond, that chemical bond simply would not form. It's that simple. Any chemical bond that forms must release energy. And because of its reciprocal, if you gain energy by forming a chemical bond, it costs energy to break a chemical bond. Your biology teachers have taught you that when ATP breaks a phosphate bond, it releases energy. That is nonsense. It is completely wrong. It costs energy to break a bond, yes, even in ATP. But if you saw the overall ATP reaction, you would see that ATP goes from ATP plus water to ADP, which has a new bond formed in it, and phosphate, which has a new bond. Breaking that bond does not release energy. I'm sorry. I don't care who says it. It's wrong. The energy comes from the formation of the new bonds in the ADP and the phosphate. That's where the energy is released. Now, if you're taking biology, don't argue with your professors, because you know you have to barf back whatever information they tell you, even if it's wrong, just to get a decent grade. But just have this little, in the back of your head. It's gonna know. It's like, okay, I know better than that, because you're breaking a bond. That's costing energy. It's the formation of the new bonds. It's releasing it. I know something my teacher doesn't. Okay. I don't really blame the biology professors, because this is what they've been taught as well. They never really stop to think about it, but they're not chemists. They're not thermodynamicists. So they just take it as granted. But it is wrong. It is wrong. Okay. If you don't believe me, by the way, if you're a biology teacher, look it up. Look up the actual reaction of ATP plus water going to ADP and phosphate, and circle the bonds that are broken and the bonds that are formed, and you're going to find the bonds that are formed. Yeah, you're going to form bonds, and those are where the energy comes from, especially the formation of the phosphorus and hydroxide bond. That's where that energy comes from, is the formation of that bond in ADP. Anyway, back to our problem at hand. In order for gasoline to burn, we have to break 16 of these, 36 of these, 25 of these. Each and every one of them will cost us energy. But the formation of these bonds and the formation of these bonds gives us that much amount of energy back and more. The way we would write this reaction Remember, delta, change in. This is enthalpy. Remember, the H is enthalpy. It's always final minus initial. So it's the enthalpy of the products minus the enthalpy of the reactants. Which in this case, let me move my eraser. I love chalkboards. I really do. Honestly, I just love them. Products are 32 carbon dioxides. So it's the enthalpy of 32 carbon dioxide, carbon-oxygen double bonds. 36 oxygen-hydrogen single bonds. Now that's how much energy is released, but remember there's a cost. If you've ever invested money, you don't get money for nothing. I have a friend who's starting to invest into the stock market. She's so smart, she's going to be a billionaire probably in the next month and a half. But it's not like you can just say, okay, I want money for that stock, because you have to buy the stock first. So if you put $100 into your stock and you get $200 out, did you make $200? No. You made $100 because you have to subtract the initial investment. And that's what this is. We have to subtract the 16 carbon, the 36 carbon hydrogen. Now this is an approximation only, and the 25 oxygen. This is an approximation, and actually there's more accurate ways to do it. But this is kind of making the point that I want. It's the formation of the new bonds minus the cost of breaking the old bonds. It's just rearranging those bonds. That's enthalpy. Now if we go back to this reaction over here, we can rewrite this. Out of space, so I need to erase. So enthalpy is how we measure heat of reaction. But we're working with pressure and volume. So we're not going to use the old definition of Q. We're not going to use MC delta T of work. PD. Work is force times distance. We're going to do something different. In chemistry, we talk about pressure. And you know what pressure is. It's a song by Billy Joel. Actually, Billy Joel did one. Queen did one. Pretty sure Sting did one. Anyway, pressure. Pressure is how hard a gas is pressing on the surface of a wall. Actually, pressure can be applied not just to gases, but to anything. The water inside this container, what's left, is pressing against the walls of the container. That's pressure. If the pressure becomes too great, or if the walls are poorly constructed, guess what? They break. That's pressure. Pressure, by definition, is force per unit area. Force divided by area. Now what's a force? Well, weight is a force. As I'm standing on my ground, I am pushing down on the ground with my weight. Mass is a measure of quantity of matter. Okay, so my mass is fixed. Well, it's not fixed because I love sweet stuff. So I can gain weight, I can lose weight. Actually, it's really hard to gain weight these days. That's a medical issue that you don't need to know about. Anyway, really hard for me to gain weight, but the mass that I have, that's how much of me there is. If I were to go to the moon, I would have the same mass because I'm still the same guy. Weight is mass times acceleration due to gravity, which here on planet Earth is 32 feet per second per second. If I go to the moon, where the acceleration due to gravity is much less, my weight is much less because I'm pressing on the moon not nearly so hard as I am here on Earth. So weight is a force. For example, when you fill up your tires on your car, you probably fill them to 35 psi. What's psi? Psi is pounds, force, per square inch, which is an area. Okay? It's psi, force per area. Now, if I take pressure and multiply it by volume, volume, several ways we can define volume, but volume is basically area times distance. So you can get the area that you're pressing on a wall times distance in this direction. Okay? So you have this is the area of my palm, okay, times however far out we're going. That's a volume. And if we look at this, areas will cancel. So pressure times volume is force. And now the star of our show. Everyone say hi, Star. Hi, Star. She just has to get her 2 cents worth in, doesn't she? See, her name is Star. That's why that's a funny joke. So if you didn't get it, she's butting in and she's a star, so she's the star, but her name is Star, which is funny, I guess. Well, you'll be laughing later when you think about it. Yeah, there she is. Anyway, pressure times volume is force times distance, which is work. Yes, we all love you. We all love the star. Okay. So in chemistry, we talk about pressure, volume, work. Now, I've said before, usually in chemistry, we do this at a fixed pressure. So pressure's not going to change, but volume might. For example, you might have a piston. So volume can change. So a change in energy, change in energy is change in enthalpy plus pressure times change in volume. Boy, did we get into the weeds. I apologize. I wanted to give you a more practical example of the first law. But that's okay. We can do this. This is fun. So pressure times change in volume is work. Work costs energy. And Joule showed us how energy can be related to temperature. Because that energy to do the work has to go somewhere. Athletes know this. Are you an athlete? Before your big match or game or whatever it is that you're doing, what do most athletes do? They have a lot of carbs, carbohydrates, sugars. It's chemical energy. Sugar is chemical energy, and they take that chemical energy in for their body because they know that during their expedition or ride or whatever they're doing, they're going to be expending a lot of energy. So they take energy in so they can spend it. Doing work. Riding that bicycle along that trail. Running the track. That's work. Force times distance. You're applying a force to the ground and you're running. Taking a football and running it through the goal. That's work. Costs energy. If you play baseball, well, baseball is a lot of standing around. So baseball isn't really a sport anyway. bit. Here's my impression of a baseball player out in the field. Okay, that was it. That piss you off? That means you're a baseball fan. I apologize. Baseball is not my game, but I'm kidding. It is. There's a lot of skill involved. There's a lot of strength. So yeah, that was just a joke. Just a joke. Don't go getting all sensitive on me now. You're a baseball player. You're better than that. It's just a joke. Anyway. So, Joule showed us that work and temperature, energy can be converted into work and vice versa. Now, here's something that you may be a little more familiar with. Did you ever grill? I have a gas grill that I hardly ever use because I am a fool. But if you've ever had friends over for a picnic and you get out your gas grill and you grill it up, well, the grill part is pretty obvious. That's this. This is your grill part, delta H. You know, you have propane, it's coming in, it's burning, releases energy. The heat, zeroth law of thermodynamics, the heat is transferred from the flame into your steak or chicken or vegetables or whatever it is that you happen to be grilling. That's just chemical. Okay, we all know that. But what happens to the tank? Did you ever think about that? Did you ever notice that? If you grill for a good long time, that tank gets ice cold, and I mean literally ice cold. Because I have seen ice form on the outside of the tank. Why is that? Well, now, inside that tank, it's not constant pressure, is it? It's constant volume. That tank is not going to change volume very much. So we can rewrite this instead of PDV. We also do work when the pressure is constant. I'm sorry, when the volume is constant, but we change pressure because that pressure is going to drop. That's work. And according to the first law of thermodynamics, work requires energy. What's happening is, as that gas is going out through the nozzle and expanding, and the gas inside the tank is decreasing pressure, work is being done. That costs energy. That energy is the reason that the tank drops in temperature. It's taking heat from the surroundings to continue to push that gas out through the nozzle and into the grill. First law of thermodynamics. Now, I want to blow your mind a little bit. How do we know that this is true? How do we know? Actually, you know what? I'm going to save that for the second law of thermodynamics. I think it fits better at the second law. So we'll talk about that at the second law. But keep in mind, you now know that biologists are wrong as a class. I have like one great friend who is a biologist, love her to death. And one of the reasons I love her is because she actually appreciates the various sciences and how they fit together. She used to come to me to ask chemical questions because she was teaching principles in class. I have known so many biologists, and I've heard them say, we don't need any other sciences because biology has it all. Wrong! You and I, we're humans. We cannot perceive the world in its entirety and all of the sciences interacting the way that they do. It is so intricate. There are so many facets that we cannot understand it. Now God, if you believe in a God, yeah, sure, God can understand it. But are you really going to compare yourself to God? Not a bright thing to do. So So as humans, we compartmentalize the sciences. I love chemistry. Chemistry is related to changes in matter. I also happen to love physics. Physics is the study of energy. Now, I love chemistry more. That's why I consider myself a chemist. But I'm pretty good at energy, which is why I'm pretty good at the laws of thermodynamics. Biology? Don't ask me a biology question, because I don't know. So how can a biologist be expected to understand biology, chemistry, physics, and anything else that they might want to throw in there in their arrogance? I've known, and I probably should not insult every biologist out there. I apologize to the ones who do not fit this category, but I kid you not. I've known far more biologists telling me that I'm a waste of oxygen than biologists coming to me and saying, you know, I need your expertise. I'm not an expert at biology. But I will tell you that biology is chemistry. Because this is matter. And what's keeping me alive? Those are chemical reactions. Something to think about. And you should really think about it until the next video, because I am out of here!